Okay, we have three types of collisions, and the first two we're going to talk about are inelastic collisions, and the second one is perfectly inelastic collisions. Inelastic collision is when two objects collide, they separate, momentum is conserved, but energy is not. Okay, and that's the key point with inelastic collisions is there is no energy is not conserved. Okay, it gets transferred to other things. So an example of this would be uh, the tennis ball dropping down, hitting the ground, and not returning it to its initial height. There's no conserved energy. Therefore, I'm gonna show you an example that from the uh, simulation that we used in the previous video. And I'm going to set this up, and we'll look at the data. We can see that the momentum before the collision, we're just going to have a situation that's inelastic. So this would be an elastic collision, which we haven't talked about yet, so you don't need to know what an elastic one is just yet. We will get into that. But an inelastic, meaning you don't have elasticity of 100%, so you have an inelastic collision that's anywhere in this range. Uh, and what's going to happen is, right now we have kinetic energy of 0.25, and our total momentum, 0.5 plus 0, is equal to 0.5. Well, if I run the simulator, okay, speed this up, and allow them to collide, what you'll see as I continue to run this is the energy will no longer be conserved, so the energy is going to drop, but the momentum is going to stay as 0.5, the total momentum. And if we look, the energy has dropped to 0.12 joules, and if we add up our two momentums after the collision, they add up to 0.5, okay? So in inelastic collision, momentum's still conserved. Momentum is going to be conserved through every collision we talk about, but inelastic, there's no kinetic energy. And with inelastic, the objects separate after the collision. Now, let's go back to the notes, and you'll see perfectly inelastic is when two or more objects collide, and they stick together. Okay, they stick together. Uh, that's the difference here. Is perfectly inelastic, the objects stick together, kind of like the baseball mitt and baseball example that we had done before. That was an example of a perfectly inelastic collision. Uh, Another one, and we'll get into another example of a perfectly inelastic next, but another example would be the brick dropping into a moving vehicle. That's a classic one is, you know, as a trucks or a car is moving along, somebody drops more mass into it, you're going to have a perfectly inelastic collision. Uh, Momentum is conserved, but energy is not. Again, momentum's conserved, but energy is not. Okay? So what does that look like? Well, that's a situation that looks like this. We'll reset this. We'll keep this at... Now, perfectly inelastic means there's zero elasticity. So they're going to stick together. We're going to see what the kinetic energy was before. These things are going to move. The momentum is 0.5. That should stay conserved. And as these things move off, as they collide, they're going to stick together. And you can see them stick together. The kinetic energy drops fairly significantly now. And but the momentum is still conserved. 0.13 plus 0.38 is 0.51. 0.5 is, roughly equivalent to 0.51. So one thing to note is that the velocities of both these objects are the same. Well, that makes sense because they're stuck together and they're moving off after the collision. They're going to have the same velocity after the collision in perfectly inelastic collisions. Okay, so perfectly inelastic collisions, the velocities of the two objects are going to be equal to each other after the collision. Uh, so that's kind of like one of the key tricks to solving a perfectly inelastic collision. And let's try solving one of those perfectly inelastic collisions. Inelastic collisions, we'll start solving a few of them as we get into two-dimensional collisions. But we're going to practice first with doing a lot of perfectly inelastic collisions, and we'll go from there. So let's take a look at an example problem. Okay, so we have a projectile with a mass of 0.2. It's fired at 300 meters per second, and it embeds itself into a target with a mass of 2.5 kilograms. So you can imagine a bullet being shot at a block of wood. Okay, so here's a bullet, and here's a block of wood. Let's make the block of wood green, or excuse me, red. So you have a block of wood. The bullet's going to get fired this way. The block of wood's just standing there, and after it gets shot, it embeds itself. So after it's shot and embeds itself into the block of wood, it looks something like this, where you have the block of wood with a bullet inside of it. Okay, and actually, I would probably move this. It's moving together. Both of them are moving this way. Okay, so after the collision, they're stuck together and they're moving off this way. We want to know what the final velocity is of the target and the bullet, and we also want to know how much energy is lost. So, the first part is, for finding the final velocity, we know that momentum is conserved. So we can use our conservation of momentum equation. So initial momentum will equal final momentum. That's our conservation of momentum equation. Just kind of matching up the purple with before, the blue with after. Initial, final. So you've, the two objects before, they've got to add up to equal the two objects after with their momentums. So we'd expand this equation to look like this, where you'd have mass. Now you have the mass of the bullet, times the velocity of the bullet initial. That's up here. Plus the mass of the wood, plus the mass of the wood times the velocity of the wood initial. That's right here. Well, the initial velocity of the wood is 0, so this whole term is 0. Okay, and the mass of the block, 0.2 times 300. And then this side of the momentum equation is going to be equal to 60. That's kilograms times meters per second. So this needs to equal the final momentum. So if you have the mass of the bullet and the mass of the wood, we already have those two numbers. We're solving for the velocity of the bullet and the velocity of the wood after. Well, because it's a combined situation, because of this, then the velocity of the bullet final will equal the velocity of the wood final. So let's just call them the same term, VF. And if we do that, then we have a situation where we have mass of the bullet plus the mass of the wood times V final. This V final is going to get us, is what we're trying to solve for. So plug in the numbers for the masses and solve for V final. V final is equal to 22.2 meters per second. Now, the next thing they ask is how much energy is lost, and we just go back to our last chapter where we talked about conservation of energy. They're looking for the energy lost or the work out And one of the things we can do here is assume that the potential energy is zero. That uh, we're going to use this uh, zero line here, the horizontal, as the zero line. So we can assume that the potential energy is going to be no loss because we're at the same potential energy before and after. Okay, so we just got to deal with the kinetic energy loss. So what our energy equation looks like is potential energy initial plus kinetic energy initial equals potential energy final plus kinetic energy final plus workout. And this is what we're solving for, this energy loss. And again, I said we can assume that these potential energies are both canceling out because we're not going to have, we can just assume that the height is zero for both of them. So what we have over here is the total kinetic energy of the system. So the mass of this object times its velocity over 2 times its velocity squared over 2 plus mv squared over 2 for this object equals mv squared over 2 for both objects in the final realm. So writing out what I said, mass of the block times velocity of the block squared initial over 2. I'm sorry, that's the bullet. This is the block, the wood block, squared. In the problem, it's the target. I'm using wood block as the target. Over 2, and mass of the bullet plus mass of the wood block uh, times the velocity final squared, which we solved over here, over 2 plus the workout. So we're going to solve, we have all of these terms. You're solving for the workout. And the velocity of the target initially is 0, so this term here is 0. Solve for workout. That becomes 9,000. This calculates to 665. Solving for workout is 8,335 joules for our workout, or the energy lost.